All right, one last short topic I'm going to kind of gloss over pretty quickly here. It's polyprotic entities. They may donate or accept more than one proton. That's implied by the name polyprotic. Okay, but this occurs as a single proton transfer that happens more than once, rather than a single transfer of more than one proton. And I'll explain what I mean. So carbonate is a diprotic base, which means it can gain a proton twice. All right, the first one turns into hydrogen carbonate. So CO3 turns into HCO3 with a proton transfer from H3O. If you keep adding H3O, eventually the pH will get to a point where this reaction occurs. But notice CO3 never just becomes H2CO3. Okay, it's a gradual process. It looks like this. If you were going to titrate CO3 with H3O, it would look something like this. Okay, so two equivalence points, not a single equivalence point getting you to H2CO3. Doesn't matter the concentration of H3O. You could be adding 10 mole per liter stuff. You're still going to see two proton transfers, not a single transfer of two. Okay, one last thing I want to say is every time there's an equivalence point, the pH changes quite a bit. Remember, pH, it's a logarithmic scale. So if the pH changes by 2, that represents a 100 times more or less acidic. So I'll show you a consequence of that. There's an acid H3PO4. It looks like it might be able to donate 3 protons. If you add hydroxide, you're going to get H2PO4. Okay, so there's a nice proton transfer there. If you keep adding hydroxide, you absolutely get HPO4. Okay, really quickly I'm going to sketch what you could get as a pH curve. So if you start with H3PO4, it'll be down here. We're adding hydroxide, we get an equivalence point. Okay, so this is H3PO4. Okay, try to frame it. Then you get H2PO4. Keep adding hydroxide, you're going to get another equivalence point. Now we're at HPO4. Okay, you guys with me so far? You may think that by still adding hydroxide, you should be able to get PO4. Okay, but what happens is this HPO4 is already really, really basic. Every time the pH jumps, you're talking about a factor of 100 or 1,000 times more basic. So you actually never get another equivalence point. This reaction is not quantitative. So you actually just reach an equilibrium system where there's a gradual change in pH. You're in a buffer zone now. Okay, so you never get a nice third equivalence point. You only ever get 2. And I hope that makes a bit of sense. So not quantitative. And again, that's because this is already strong. It's not a strong base, but it's a strong weak base. This is already very basic. It does not react quantitatively with OH. Or you might think this is such a weak acid. All right, that's a better way of thinking. It's such a weak acid, it hardly accepts or hardly donates protons to hydroxide.